So hope you're still able to listen. I'm going to present a little case study with you in Cumberland. It's part of my study for this semester. And I think it's in the beginning, I thought it's a little bit out of topic for this workshop, but during discussions, I experienced that it may actually fit in quite well into the topic here. Yeah, let's go into it. First, I want to introduce our project team. It's quite international. We have a French participant, me representing Switzerland, and 3 Canadians working on that. There's an open position for spring term because I'm going to leave. So if anyone feels like joining, maybe Sophie. Yeah, drop in your resume, I guess. Yeah. So before deep diving into the slides and stuff I'm going to talk about, I want to outline what I'm actually going to present. So as I assume not many people are familiar with the project I'm going to present, so I have to do that. Then I'm going to do a little bit of a theoretical input about the modeling tool we use to do that. I have to talk about thermal networks and mine water thermal energy storage for some seconds, just to get all on the same page. Then I can talk about a case study, share some first results. They are very, very, very first results, so don't take them for granted. And to finish off, there's a future development going on with the modeling tool, and I think this fits into the discussion we just had in the previous presentation. So first, this project was initiated by the mayor of town of Cumberland. She approached ACET with the idea of using the mines below town as a heat source for the heating systems there. While involving this project this semester, it turned out in a more industrial use case where we have a good input because still only 20% of the energy used in industry is electrified. And the idea is to use these mines to sort of push to more renewable aspect or a renewable share in the industry sector now. And with the learnings from that site that is just close to Cumberland, we can go back to the mayor of town, share these learnings, and give her a base for discussion with the town to sort of implement the system back then also in the downtown area. So where do you find Cumberland? I think it's 4 hours drive north of Victoria on the island. On the right image, you see depth maps of these abandoned coal mines below the town and below the industrial site. And if you zoom in into the industrial side, there's a landfill just close by as well. This is a bit of a geographical location. And the idea is, or was in the head, to use the natural gas that is leaking out of this landfill as a source of natural gas for the industrial side. This is still a bit in the head, but I think the project scope already changed on Friday again. So it's research, it changes all 2 seconds, I have the feeling. Yeah, speaking about the state that was before Friday. So for the moment now, there's only the yogurt factory present on the industrial side. The rest of this development is to be developed by the next couple of years. So we are very free in ideas on how we can develop this industrial site. The idea is now to implement a greenhouse next to the factory to grow fruits and plants that go into the factory again for yogurt production, as well as having a share for the community of Cumberland. They have a bit of an agriculture background as well, not only the mining background. And to get the heat for the mine and for the greenhouse, we install containerized data center units. That means we can step up the development and the data center capacity hand in hand to meet the demand on both sides. I will explain that a bit more in the case study. Just give an overview about what's actually going to happen here. These boreholes there pointed out on the map, they are used to the connection into the mine. So data center is cooled via the mine water. We can extract this mine water on a later stage for additional heat use on site. That's the key idea. Yeah, so as we are just having this one fixed point of the factory, we know we have some grid electricity. We could add photovoltaic to the system. We could add the waste heat. We have natural gas as a potential source. The system is a black box. We don't know how the system looks like yet. But with the so-called PiHub tool, we can generate outputs to get the best interaction of all these sources in a time series aspect or as a summary of a whole year, for example. PiHub was started in 2017 as an open source energy hub modeling tool as part of IESVic of the institute here. These energy hub models are very useful if you don't really know how the system looks like. You can have a lot of assumption and you still get a good understanding of the interaction of a different form of energy in it. And for us, this is also very helpful as it's still a feasibility study. We can see how that could work. The model is linear. This is also a bit of a limitation to it. But on the other hand, it's very fast and easy to solve. For those of you who know about linear optimization, it's a multi-integer linear program. You can use Gürber that is commercially available, for example, or to keep it open source, CPC is implemented, so you can solve these problems. So what can we actually model with PiHub? If we have a lot of operational degrees of freedom, meaning different energy streams, we can look on storage units. If they're, we can set them to use as a short-term storage or seasonal storage. We can do selection of converters. Converters are in this term, for example, a gas boiler or a photovoltaic plant. These are converting energy from one to another form. And we can optimize for a certain metric and also look on the whole network and optimize that. Limitations, as already mentioned, we have to see that the whole thing is linear. That means we cannot have, well, I don't know, it's still a matrix equation that is solved, being very general. So we cannot have complex interactions between each of these energy streams. And we have to limit the number of integer variables. That means, for example, if we have different optimizations, operational behavior of one component, we can switch between these behaviors. And by switching, we have like a 0 and a 1 that selects or deselects it. And this explodes the whole problem. This limitation. And as I just started using PiHub in September, the one observation from my side was that I'm not able to size a demand. Demand is still an input. I cannot give a normalized profile to demand and size the capacity of it to fit the model. You have to write the model in different direction that's not a demand anymore. Then you can optimize for that, for example. So, excuse me, this is the most mathematical slide you're going to see now. Basically, an energy hub model consists of nodes and links. Inside the nodes, there's the energy transformation happening. Very generally speaking, it solves this matrix equation of the output is the input time the conversion factor. Conversion factor can be seen as an efficiency, for example. If you have a gas boiler, input is gas, you boil it, you heat it, maybe 40% efficiency, then you get the heat out. But we can also combine several input streams. We can also model a heat pump, for example, and we can add storage quantities to the node. For those of you who like schematics, this is how such a node can look like. Can be pretty chaotic if you try to look at it. And if you only look on, for example, the domestic hot water generation, you could think, okay, I could install solar thermal energy. I could also install a gas boiler to provide it. And I need the storage. Another question is, yeah, what's the optimal size for all of these things? Or do I actually need all of them? And we can solve for example, minimal costs or minimal emission, and then we get different results based on the metric. And to have the interaction between different nodes, we have the so-called links. These links are made to carry different types of energy. It can be electricity, can be heat, can be whatever you can think of, natural gas, for example. So we can link between different nodes and create a network. And also, as mentioned, in order to solve the whole problem, we need an optimization metric. It can either be costs or carbon, but you can also come up with any other optimization metric you want and optimize for that. That's it with PyHub, how the tool works internally. In order to introduce a case study, I have to talk about the 4th and 5th generation thermal network. The 4th generation is one that we actually think have a good feeling for it. If you have to distribute heat and cold, you have to have a supply and a return line for both of these quantities. A 5th generation network, as the temperature is much lower, only needs one supply and one return line. And the consumers are not consumers anymore, they're so-called prosumers. So take heat and produce cold, and if you take cold, you produce heat. And the goal is to keep as a good balance as possible of heat and cold, so don't need to provide so much energy into the network itself. As you, in a 4th generation, you have to provide the whole heat demand via an energy central. And these mine water energy storages, thermal energy storages, in a very simple case, they can look like this. You have abandoned mine seams, and you drill to 2 seams, for example. You use one seam as a warm reservoir, the other one as a cold reservoir. And based on your demand on the surface, you cycle from cold to warm or from warm to cold. And this is an image from Scotland. This is one of these coal mines. It seems like it's mirrored, but this is the water level. And basically, as you could think of, it's really just like they pump hot and cold and warm water from one to the other tank. And that's how you generate or use it above the surface. In the case study, we have both of these district thermal networks. One is connected to the data center, the other one is connected to the mine water storage. I'm going to talk you through the schematic, so you don't have to try in your head. What we see now is just like the data center plus a storage unit to buffer the load from the data center for the waste heat of the data center. If there's a surplus in energy, in heat, and the greenhouse and the process heat in the factory is always satisfied, we can send it down to the mine to have a cooling that doesn't use any water itself. You don't have free cooling units on your data center. You just pump it into the mine. If you have less waste heat produced by the data center, there's this gas boiler that's supposed to work as a peak, just to cover the peaks in these times. On the consumer side, we have the greenhouse that takes some, and the process heat in the factory. Below, we have the mine, that is the heat sink for the data center or the heat source for the floor heating for other consumers that also can be thought to be in the loop on this industrial side. And we can also provide the cold applications on the industrial side via this 5th generation network. The output of the Pi-hub energy hub model can look, for example, something like this. So you get like the storage level of this storage next to the data center over the whole year. The result from this plot was created in 5 to 10 minutes with the Gürber solver. So I think it's really fast to solve 8,760 time steps. But it's a bit of a sort of, not a pity, but if you optimize for cost, you get a very hardcore solution. So it's not, you don't have to look on the plot itself. I think more the idea of you solve for optimized costs, for example, and then you relax this hard constraint, maybe 5%, and solve the problem again with the objective that the maximum cost can be a little, this 5% higher. And you see how much carbon you can reduce or how does the system interact with that. And it looks very weird for me now. I think it's because the data center is so expensive. If you release the costs a little, it will add more capacity to the gas boiler because also the storage is more expensive. So, but this is more my side. I have to go back to the model and try to figure out how this can be done to install more data center capacity rather than more gas capacity. But it's more the idea of just because a solution is optimal in a model doesn't mean that it's actually the best solution you can have. So I think this working with cost relaxation plots is a good approach to also communicate results to industry and to customers. The future development of this whole energy hub tool. If you know Python, you probably can read a bit of the code here. If you don't know Python, I'm sorry. So Rolf, who developed this, initiated the idea of the energy hub in Python, has come up with some sort of a drag and drop solution with the Pi-hub, which I find is a really good approach to communicate these tools that are used for research to a broader community or more people in industry as well. Because drag and drop, everybody can operate, and you usually have your idea in the head what you want to model, but you don't know how to do it because you cannot type Python or type any other sort of code. And for most part, just doing this, it's also visually available. You see what you have done. It's easy to communicate as well. But it's also very first stage. Just a screenshot from what he did in a couple hours. But I think it goes in the right direction to sort of get these tools out in industry or also the other communities to work with and not keeping them just for research purposes on its own. Yes, I hope you're still awake and happy for questions.
Things come to mind. First, just a little bit more context. I think rather than thinking about this like one passive monolithic data center approach to this like a network of distributed boilers for industrial processing. So in that sense, like I think a big opportunity here with modeling is like matching how you can connect a given industry and a given industrial use to the right scale of compute. And then also kind of that industry operators need for on-site data storage, data processing, but also eventually that need to run their operation. So you're essentially extracting two value streams with your same consumption of electricity. And the ultimate goal here, like as discussed with the developer and the coach, is to kind of come up with a phase plan where these undeveloped industrial lands can kind of produce recommendations on the next most viable to add to the industrial park based on the built out district. The modularity, I just want to stress like the beauty of the model that Pascal has developed and also the uncertainty strategies that Kenzie is working on is that we're really looking at adding that next module of compute. How and where does it make sense in coordination with the growth of the industrial parks? But I think PieHub has been a great tool for that that opportunity, and I just want to commend Pascal for getting into the weeds, learning like remotely through Zoom with the postdoc who developed this application with Ralph and getting us to this point where now we can ask these really interesting questions about how industry can work in
Yeah, I think I want to add here that as we have just like one fixed point in the whole model, the only actual demand we had was an electricity demand from the factory itself. Then it's very valuable, I think, the work Kenzie does with this whole uncertainty study in these models, because just because I have literature, I know I can disaggregate this electricity demand from the factory into heat and cold, and via heating degree days, I can estimate the heating demand or heat load profile. Doesn't really mean it's super correct. I mean, it's totally wrong for sure. But then it's super valuable to know how wrong am I, or how does the model react if the heating demand is 10% more or less? Is the output also just 10%, or is it basically only 2% in the end? It's to have this interaction is very, very very valuable also for further steps in not on this particular project, but general project that start with very, very low data sources, and then you try to get your stuff on the way. You have to have a feeling for what is the next one you have to get. Because you see this one changes nothing basically, so you can leave it, but this one has a huge influence, and you only see that through these uncertainty studies that you conduct after you have written your model. Yeah.
Would this work for other thermal energy storage techniques, like the modeling that you've done?
Like storage units, or
you know, like we were talking about heat batteries earlier on. Like, would this kind of modeling work for that?
yeah, well, it depends how detailed you want to have it. If you're interested in the storage behavior very detailed, then no. But because in PieHub you don't model temperatures, and if you're only interested in how much capacity does a storage need and how does this energy change react on a system level, then it's a super good tool to use. But if you're interested in really like, hey, I don't know, I need 70 degrees on the top and 20 on the bottom, and how does this temperature change? And then I think you go back to console or whatever numerical softwares to get the temperature profiles in it. As long as you're not interested in temperatures, you can do anything with PieHub. There's a bit the same issue with the mine water storage, because the interaction with the soil is also a big unknown, but we cannot model temperatures in the model. So for now, it's just we dump heat in, we take heat out, and we do via post-processing. Like the assumption is now it acts as a sink and a source, and via post-processing of the data we got out of the model, we see how far we are off of this assumption, or how do we need to have a more detailed numerical model of the subsurface structure, or can we actually work with PieHub in the next step as well? Yeah.
If you're just kind of like dumping energy and temperature, that energy out, like how are you looking at losses in the system?
Yeah. So there are many different links available, and you assign a soil temperature, you assign a network temperature, and it calculates like a static energy loss for these links. So through, you say like your network is stable at 45 degrees, for example, and the soil is constant at 10, then you can calculate this value of the heat loss, and it's constant for the whole system, which is fairly accurate for thermal networks, to be honest, because temperatures change like maybe plus or minus 2 degrees in the network that is distributed. To represent that a little bit, you could add a storage unit on top of the network to say this has this capacity of the network volume times heat capacity times temperature difference. Then you also have a little bit of this thermal inertia in the district thermal network as well. So there's a lot of workarounds to model a little bit about temperature, but you cannot type in values for temperature. Not exactly.
You mentioned the possible source of renewable natural gas from the methane or the landfill methane next to the site. Can you speak a little bit to the versatility in terms of like if that's not a natural gas boiler, a biogas boiler, like we can kind of swap in other backup energy sources, and it becomes a slightly more flexible tool. And I'm impressed and kind of excited about some of the overlaps because with Anthony's presentation, I didn't realize that this other open source tool also can model these thermal energy spaces.
Yeah, fancy. Just to make it a bit clear how easy it is to change from gas boiler to heat pump. So this is how I've defined this gas boiler, for example, and you can just change the input and outputs and the efficiencies, and then you have a total new component inside the model. So if you have it's personal experience, it's very hard to get your head around it. Once you have it, it feels pretty easy to adjust the model then. But still, I'm running from question to question in the end. So it is easy to use, I think, if you can use it a little bit, but you have to get used to using it. And that's, I think, as well, pointing out to this here, so much easier. Yeah. More questions in the room?